Hey guys, welcome back to another round of chemistry notes. In this video, we're going to talk even more about our chemical equations and how to classify them into different types. So your first type of chemical reaction is a synthesis reaction. And synthesis means to create, to build up. So in a synthesis reaction, you're going to have two or more substances combining to form a new substance. So the sort of generic form of this is that you have A plus B coming together to create C. And you might have 3 things coming together to make something, or 4 things, or 5 or 6. You might have 18 things forming 4 things. But in any case, you're having substances combine, so your number of reactants will always be greater than your number of products. So here we have 2 types of reactants, 1, 2. And we have 1 product, just that one, and that's always going to be the case. Your reactants, your number of reactants, your types of reactants will always be greater than your number of products. Your second type is called decomposition. This is pretty much the exact reverse of synthesis. You have one, instead of building up to make something larger, you have one large substance breaking down into 2 or more simpler substances. So, since this is pretty much the reverse, your number of reactants here will always be smaller than your number of products. So here we have 1 large reactant breaking down into 2 products. And again, it could be breaking down into 18 things. That's still going to be more products than reactants. Your third type of reaction is a single replacement. And single means 1, right? So in a single replacement, 1 element replaces another one in a compound. So here we've got A by itself and B and C paired together to start with. But then when we're done, A and C are paired together and B is off by itself. So what's happened is A has come in here and it's kicked B out. B has had to go somewhere else. A has replaced B as the partner of C right here. We have 1, 2 products to end with. So that's going to be true of your single replacements, is that your number of reactants will be equal to your number of products. That's 3 down. There are 2 more to go. Your fourth type of reaction is a double replacement, which is a lot like a single replacement, but with 2 things. In a double replacement, ions in 2 compounds trade places to form new compounds. They're replacing each other. So here, A and B are paired up and C and D are paired up to start with, but then B and D trade partners. D is going to come over here and pair up with A in the end, and B will come over here and pair up with C in the end. Notice that the elements that were in the front, A and C, are still in the front, A and C. The elements that were in the back, B and D, are still in the back, B and D. Just keep that in mind. And just like the single replacement, the number of reactants we started with, exact same as the number of products that we're going to end with. All we're doing is trading places with 2 things. All right, and your last type of reaction, this is really the most distinctive type, is combustion. This is when a substance combines with oxygen to produce water and carbon dioxide, CO2, while releasing, and if you think about what combustion is things exploding, catching fire, we're going to also release light and heat at the same time, because that's what fire is, light and heat. So this can look sort of 2 different ways. This one's a little harder to give a generic equation for. Your substance is either going to be some amount of carbon and some amount of hydrogen, or some amount of carbon, some amount of hydrogen, and some amount of oxygen coming together, combining with oxygen gas to produce CO2 and H2O. In your notes, I think it says reactants right here, so you might want to correct that to products. That's a typo. My apologies. Your products in these reactions will always be water and carbon dioxide. If you've got a reaction that starts with something plus oxygen and ends with carbon dioxide and water, it's combustion. It is. So let's practice identifying these. Let's see some examples. Here we've got solid zinc reacts with hydrochloric acid, HCl, aqueous, to produce zinc chloride aqueous and hydrogen gas. We are given the blanks. We are told to balance the equation. We can do this in either order. Let's go ahead and just balance it first. Over on the left, we've got Zn, we have H, and we have Cl. Over on the right, we have Zn, we have H, and we have Cl. On the left, we have 1 zinc, 1 hydrogen, 1 chlorine. On the right, we have 1 zinc, 2 hydrogens, and 2 chlorines. So we need to do something about these two over here on the left. The easiest way to do that is throw a 2 right in there. And then we'll have 2 hydrogens and 2 chlorines, and now it's balanced. So you can leave these other blanks empty. You can fill them in with 1s, either way. The next thing we need to do is identify the type of reaction. So we're starting with 2 reactants. We're ending with 2 products. That means it is not synthesis because we didn't decrease our number, and it's not decomposition because we didn't increase our number. Nothing here is building up, nothing here is breaking down. There is no carbon in this problem. There is no oxygen in this problem, so it is not combustion. So that leaves us with either a single replacement or a double replacement. The fact that we start right here with a single element all by itself, that single element means it's a single replacement. You can't have a double replacement if you start with a single element. What we have here is zinc coming in and kicking out this hydrogen. The hydrogen goes off and does its thing. So when we're done, we have zinc paired up with chlorine, and we have hydrogen off by itself. Notice that things don't look exactly the same. We don't just have zinc and chlorine jammed together. We're still accounting for the fact that zinc has a 2+ charge and chloride has a 1- charge when we create this formula, and we've accounted for the fact that hydrogen is diatomic. So when you're creating your products, you are going to have to actually think about what those products are. It's not time for that just yet. That's the next video, but just be ready. Be aware it's coming. As far as this problem, this is a single replacement. You may sometimes also see them called displacements. A single displacement. All right, 1 down. Let's look at another example here. Our next one, we have C3H8 reacting with O2 to produce CO2 and H2O. This is the type of problem that you should sort of just be able to pick out off the top of your head. Just on sight, you should recognize this one because here we've got carbon and hydrogen together. That's called a hydrocarbon, reacting with oxygen to produce carbon dioxide and water. That is the very recipe for a combustion reaction. It is made entirely of carbon, hydrogen, and oxygen. The products are CO2 and H2O. Your reactants involve something reacting with oxygen. Straight up combustion. Easy one. So good news, bad news about your combustion problems. They are the easiest to identify, and they can be among the trickiest to balance. That oxygen can cause some problems. So let's go ahead and take a look now at balancing this. We've got carbon, hydrogen, and oxygen on the left. We have carbon, hydrogen, and oxygen on the right. Here we've got 3 and 8 and 2. Here we've got 1 and 2. And remember, we've got oxygen here and oxygen here for a total of 3 oxygens. So now we've got 3, 8, 2, 1, 2, 3. Awesome. Nothing is balanced. Remember that one of the tips that we learned when we first started talking about balancing equations is that when you have carbon, hydrogen, and oxygen in a problem, you want to balance them in that order. Carbon, and then hydrogen, and then oxygen. So looking at carbon first, we've got 3 here on the left and 1 here on the right. So if we put a 3 right here, that'll bring us up to 3 carbons, but it'll also affect our number of oxygens. That'll give us 3 times 2 is 6, plus this one over here is 7. So that means that carbon is now balanced. Hydrogen and oxygen, not so much. So carbon, all set. Let's take a look at hydrogen next. We have 8 on the left and only 2 on the right. But if we put a 4 right here, that'll give us 4 times 2 is 8 hydrogens and 8 hydrogens. So that's good. But it has also now affected our number of oxygens. Now, this is all gone. We've got 3 times 2 is 6 oxygens plus 4 from over here gives us 10 oxygens. And if we put a 5 right there, that'll give us 10. So we've got 3, 8, 10, 3, 8, 10. We can put a 1 here or not. That is your choice. This is a combustion reaction, and we are all done with this problem. Let's take a look at our next one. So here we've got solid potassium chlorate produces potassium chloride and O2. So this again is kind of an obvious one to see because we're starting with one large thing breaking down into 2 smaller things. Off the bat, we can see that this is a decomposition. And that's in fact usually how it's read is potassium chlorate decomposes to produce potassium chloride and oxygen. So now that we've identified this is a decomposition reaction, a breaking down into smaller things, we can focus on the balancing. So here we've got potassium and chlorine and oxygen, potassium and chlorine and oxygen. So here on the left we have 1 potassium, 1 chlorine, 3 oxygens. Here we have 1 potassium, 1 chlorine, and 2 oxygens. So potassium and chlorine are all set, oxygen not so much. And we've got that great situation where there is nothing we can put in this blank here to create 2 oxygens, and there's nothing we can put in this blank here to make it be 3. But if we put a 3 here and a 2 here, then we'll get 2 times 3 is 6 oxygens, and 3 times 2 is 6 oxygens. However, over here on the left, adding this 2 in here changes this to be 2 potassiums and 2 chlorines. Versus over here on the right, we have 1 and 1. So if we throw a 2 in this blank here, that'll bring us up to 2 and 2. Oxygen is still 6, and that is balanced. All right, so that's our decomposition. Something I have not been doing that you should always do, double check, make sure that we didn't overshoot somewhere, that we can't divide our coefficients by a common factor. 2 and 2 and 3 do not all have a common factor, so we don't need to worry about it, but just remember to keep an eye out for it. All right, number 4, this is a little messier. Here we have barium chloride reacts with potassium iodate to produce barium iodate and potassium chloride. Even just in reading that, you might start to pick up on what type of reaction this is, but we can still process of elimination it. It's not combustion. I'll give you that one for free. We started with 1, 2 reactants. We ended with 1, 2 products. So that rules out synthesis and it rules out decomposition. So once again, it's going to be one of our replacements, either a single or a double. Nowhere in this reaction do you see one single element by itself. Here is a compound, and a compound, and a compound, and a compound. We've essentially just had our chloride and our iodate swapping places. And if we've got two things trading places, that's going to be not a single, but a double replacement. And your double replacements, really either of your replacements, this is where it's going to be really helpful to keep your polyatomic ions together. So we've got barium and chlorine and potassium, but instead of splitting this up into iodine and oxygen, since things are just trading partners, we have iodate in our reactants and we have iodate in our products. So to balance this, we can leave this as iodate. That'll make things a little bit easier. And then here, barium, chlorine, potassium, and iodate. On the left, we've got 1, 2, 1, and 1. Please don't put 3. Remember, the 3 is part of the iodate formula, and of this IO3, there's only 1. And over here, we've got 1, and 1, and 1, and now there are 2 because it's in parentheses with another coefficient outside. All right, so barium, 1 and 1, that's good. Chlorine, we have 2 on the left and 1 on the right. That's not ideal, but if we put a 2 right there, that'll bring us up to 2 chlorines and also give us 2 potassiums. So then over here on the left, barium's all set, chlorine's all set. Now we have 1 potassium in our reactants. We have magically created a second potassium for our products. That's not okay. But if we put a 2 here, that'll bring us up to 2 in our reactants and also give us 2 iodates in our reactants, which we also have in our products. So that's good. We can, again, leave these blanks blank or fill them in with 1s, either way. So this is 1 mole of barium chloride reacts with 2 moles of potassium iodate to produce 1 mole of barium iodate and 2 moles of potassium chloride in a double replacement reaction. Always good to practice using your words. All right, last but not least, here comes our 5th example. If you've been paying attention, you might know what it's going to be. All right, so here we've got carbon reacts with hydrogen gas and oxygen gas to produce C2H6O solid. Now, if you're just trying to go through these really quickly, you might be tempted to call this combustion because it's made entirely of carbon, hydrogen, and oxygen. However, if you look at it for more than a second and a half, you will notice that the products are not carbon dioxide and water, so it cannot be combustion. What it is we have this element and this element and this element coming together to form something larger. We have 3 reactants combining to form 1 single product. That's got to be a synthesis reaction. So once again, we'll go ahead and balance. We have carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Here we have 1 and 2 and 2. Here we have 2 and 6 and 1. So looks like nothing is balanced here to start with. Remember, if you have these 3 together, you want to do carbon and then hydrogen and then oxygen. So let's look at carbon first. So if we put a 2 in front of carbon, that'll give us 2 and 2, which is good. And then hydrogen, if we put a 3 here, then that'll give us 3 times 2 is 6, and that's good. And then on the left here, we've got 2 oxygens and 1 oxygen on the right. So we'll need to put a 2 here to correct that, and that'll give us 2 oxygens. But it also affects our other elements. And now we've got 2 times 2 is 4 carbons, and 2 times 6 is 12 hydrogens, and now it's messed up all the work we did over here. So I will tell you there's a more strategic way we could have worked this problem, but I actively didn't go through this because sometimes you'll have to go back and forth on these a little bit to make sure everything balances out correctly. It doesn't mean anything has gone wrong, you're just not quite done yet. So now we need to go back. We need to have 4 carbons on the left and we only have 2. So let's take this 2 out and replace it with a 4 carbons. And we need to have 12 hydrogens. So let's take this 3 out, replace it with a 6, and now we'll have 6 times 2 is 12 hydrogens. And now we have 4 and 12 and 2, fill a 1 in there, 4 and 12 and 2, everything is good. This is our synthesis reaction, and we are done with this problem. All right, so next up in your book, you have 6 practice problems where you'll have a chance to practice identifying what type of reaction you're looking at and then balancing that reaction. So go ahead and pause the video, work through the practice. When you're ready to check your answers, unpause. All right, hopefully this is what you ended up with for 1 through 6. Obviously, I did not write out the entire balanced equation. The numbers you see are the coefficients in order that you should have found. This is a format that you should be comfortable with. So sometimes you'll just be given 2, 2, 3, and you should understand that means that the coefficients in order of the equation you were given are 2, and then 2, and then 3. Hopefully this is what you ended up with. If not, go back, see if you can figure out what went wrong. Otherwise, feel free to move on and learn how to predict the products of these different reactions. That's what comes next. As always, good luck and happy studying.